Thermodynamic processes. We'll next look at 4 different types of thermodynamic processes and their effect on the internal energy of a thermodynamic system. In fact, we've briefly touched on 3 of these: isothermal, isobaric, and isochoric. Adiabatic is a new type of process. Well, let's look at them in a little bit more detail. Each process takes place in a situation where a particular thermodynamic quantity is fixed. First, we have isothermal, meaning constant temperature. That is, the change in temperature is 0, or T is a constant. Isobaric means constant pressure. Iso comes from the Greek equal, and baric relates to weight or pressure. So equal weight or pressure. We next have isochoric, meaning constant volume. Again, this comes from Greek equal space. And then finally we have adiabatic, which means not to be passed through. That means no heat is added or removed. So briefly, the way we look at these is we could say isothermal is change in temperature equals 0. Isobaric is change in pressure equals 0. Isochoric means change in volume equals 0. And adiabatic means Q equals 0. If you keep these handy, you can use them for solving a lot of thermodynamic problems. Let's first consider isothermal processes. In an isothermal process, the temperature is constant. That is, the change in temperature is 0. For an ideal gas, since the internal energy depends completely on the temperature, the internal energy must be a constant. That is to say, the change in internal energy is 0. If we put this into the first law of thermodynamics, that the change in internal energy is the heat applied to the system and plus the work applied to the system, we find that 0 equals Q plus W prime, or the heat that goes into the system equals negative work done on the system. Another way of looking at that is the heat into the system is work done by the system. So all heat added to the system in an isothermal process is converted to work by the system. And here is a pressure versus volume diagram for an isothermal process in an ideal gas. And as you can see, it follows this hyperbolic form. The pressure is proportional to 1 over the volume. Next, let's look at isobaric processes. In an isobaric process, the pressure is constant. Delta P is equal to 0. Now, since the work done on the system, W prime, is the external pressure times the change in volume of the system, we can see that work is done as soon as the volume V changes. Now, T is allowed to change, so we know that the internal energy is also allowed to change. That is to say that delta U is not equal to 0. Now, if we go back to the first law of thermodynamics, delta U equals Q plus W prime, we can rearrange it to look at the impact that heat has on the system. So we have Q is equal to the change in internal energy minus the work done on the system. Another way to put this is the heat that is applied to the system changes the internal energy and is converted to work by the system, i.e. delta U plus W. Again, heat added to the system will cause the system to do work, and it will increase its internal energy, and therefore its temperature. And if you look over here, we see a PV diagram for this type of process. And as you'll notice, We have a horizontal line from A to B as the pressure is held steady and the volume changes. Our next process is an isochoric process. Now, remember, an isochoric process means the volume is constant. The change in volume is zero. Now, that means that the pressure and temperature can change, and since the temperature can change, the internal energy can change. But since the work done by the system or on the system is pressure times change in volume, and change in volume is zero, no work is done. And therefore, when we go back to our first law of thermodynamics, delta U equals Q plus W prime, there's no W prime. And we're left with the change in internal energy is equal to the heat added or removed from the system. So heat added to the system increases the system's internal energy and will also increase its temperature. So what we see here, a classic isochoric process, is a vertical line. The volume is held steady as the pressure increases. As the pressure increases, you can imagine different isothermal lines and that you're moving from one to another, from A to B. So temperature increasing as well. Our last thermodynamic process is the adiabatic process. In an adiabatic process, no heat enters or leaves the system. That is to say, Q equals zero. Now, since Q equals zero, the first law of thermodynamics, delta U equals Q plus W prime, simply becomes delta U equals W prime. So in an adiabatic process, any work done on the system increases its internal energy. Any work done by the system decreases its internal energy. Here on the right, we see a depiction of an adiabatic process. You can notice how it goes from one isotherm to the next, and note also its curve. You can see that the work done by this is going to be related to the change in temperature or internal energy. On this slide, we summarize the thermodynamic processes. You may find this helpful when you are trying to answer questions or solve problems in thermodynamics. So first of all, isothermal processes. The condition is that the change in temperature is zero. This also means that the change in internal energy is zero. So the first law takes the form 0 equals Q plus W prime. Remember, the W prime is work done on the system by an outside force or outside pressure. The next process is the isobaric process. The change in pressure is zero. Here, the change in internal energy is just the heat and the work done on the system. In other words, we're seeing the original form of the first law of thermodynamics. In an isochoric process, the change in volume is zero, which means that the work done by the system or on the system is zero. And this leaves us with the change in internal energy is equal to the heat in or out of the system. And finally, the adiabatic process, where no heat enters or leaves the system, Q equals zero. And consequently, the change in internal energy is equal to the work done on or by the system.